Self-induction. Definition: self-induction is the phenomena of production of induced EMF in a coil when a changing current is passed through it. Here, two situations are shown. This is battery, this is coil, this is key. When it is closed, then current due to battery flows in this direction, then induced current will flow in this direction, which will oppose it. Similarly, when switch is opened, then current due to battery will become zero. Then this inductor will induce the current in the direction of the current of the battery. So this is due to self-induction. Now let's find out the coefficient of self-induction. So change in magnetic flux is directly proportional to current. So we put a constant. So phi equal to Li, where L is coefficient of self-inductance. Its unit is Henry, capital H. Henry. Now let's find out induced EMF. So induced EMF equal to minus d phi by dt. So minus d upon dt of phi is Li. L is a constant. So that will be equal to E equals minus L di by dt. Now, let's see the experiment to demonstrate self-induction. Here, this is coil, this is bulb, this is battery, this is rheostat, means variable voltage, this is key. Now, in this experiment, take here, I'm going to describe the experiment, then I will tell the result. Take a solenoid having a large number of insulated wire wound over a soft iron core. This is coil. Here there is soft iron core inside. This is also called choke coil. Connect the solenoid in series with a battery, a rheostat, and a tapping key. Here, this coil is connected to battery. This is rheostat, and this is tapping key. Now connect a 6-volt bulb. This is bulb in parallel with the solenoid. This is connected here. Press the tapping key and adjust the current with the help of rheostat to make the bulb glow faintly. When this key is pressed, then this bulb glows faintly. As the tapping key is released, the bulb glows brightly. When this key is released, it means circuit is broken. In that case, this bulb glows brightly. This is due to self-induction. When current due to battery is suddenly switched off, then this coil sends the current to recompensate the lost current. So as the tapping key is released, the bulb glows brightly for a moment and then goes out. This is because as the circuit is broken, suddenly the rate of change of magnetic flux linked with the coil is very large, and hence large self-induced EMF and current are produced in the coil, which makes the bulb glow brightly for a moment. This demonstrates the concept of self-induction. Now, let's derive the coefficient of self-inductance of a long solenoid. So here we are going to consider a long solenoid whose length is L and area of the turn is pi r square, where r is the radius, and it has, suppose, n turns per unit length. Now, if at any instant current I flows through it, then magnetic field inside the solenoid is given by B equal to mu naught n I. So magnetic flux linked with each turn, so flux phi with each turn will be equal to BA, that is mu naught n I times A. where A is area cross section. As I told you, it is pi r square, any turn, not area cross section, but area of the turn. Now we have to find out total flux. So total flux will be equal to, say we write it like phi 1. Now this we write as phi 2 total flux, or we can write it as phi. So phi will be equal to flux linked with each turn, flux with each turn times number of turns. So flux linked with each term is mu naught NIA times number of turns will be N times L. So N times L, because N turns per unit length and length is L. So total turns will be NL. So it will become mu naught N square A I times L. But we know that phi equal to Li. So we can compare this one, because this is expression of phi. This is also expression of phi. So I can be cancelled, and what is left? That is coefficient of self-induction. That is L equal to mu naught N square A L. But total number of turns equal to number of turns per unit length times length. So small n is equal to capital N divided by L. So if we write this value here, so mu naught, this will be N square AL divided by L square. So one L will cancel out, and we will be left with mu naught N square A divided by L. Now, if there is material, suppose iron or any other magnetic material, in that case, the value of L will increase the number of times of permeability of that material. So we can say in that case, L will become, suppose, relative permeability of the material inside the solenoid is mu r, that we have inserted, times mu naught times N square A divided by L. So now let's see the dependence of L on various factors. So from this formula, we can say that if L equal to mu r mu naught times N square A divided by L, so clearly L depends on number of turns, square of it means L is proportional to N square. Area cross section, L is directly proportional to area of cross section, and L depends on relative permeability mu r. So we can say the self-inductance of a solenoid increases mu r times if iron core of relative permeability of mu r is inserted inside the solenoid. Thank you for watching.